Hello, everybody. Today we start our first seminar with Professor Kaoru Ono from the Research Institute for Mathematical Sciences of the Kyoto University. His talk is on Lagrangian Floer theory for symplectic orbifold, and that is a continuation of his last week Edward Chase lecture seminar. Yes, please.
Thank you very much. So today I want to explain a little bit about Lagrangian Floer theory on symplectic orbifold. And I have to explain what it is. And so I have to really explain the players in this. But before doing this, maybe I just want to tell you some frameworks. So here I consider just a closed symplectic manifold. So we close symplectic manifold. And here I consider then this closed symplectic orbifold, or maybe V manifold. And here I consider so-called something related to the closed strings, and here something related to open strings. So here we have Gromov-Witten theory, or in particular we have this quantum cohomology, and they are mathematically developed by Ruan in a semi-positive case. And in general, maybe I and myself and Junli and Wang Tian, and then Ruan and Gibot, and so on. And for open strings, so here actually I have a kind of open path, so therefore you have a boundary conditions. So boundary condition is actually given by Lagrangian boundary condition in this case. So that is Lagrangian Floer theory. Including something called Fukaya category. And so this one is certainly started by the monumental work by Andreas Floer, and then there are some developments, and then in general, it is actually one by Fukaya, and then O and Ota and myself. And so I may just briefly sketch these two things later. And here, actually, maybe what is called orbifold Gromov-Witten theory, or maybe orbifold quantum cosmology. So this is actually due to Wang, Chen, and Ruan. And so what I'm going to talk about is this part. But if some sort of Lagrangian is contained in a regular part of the symplectic orbifold, in this case, actually the story was already performed by Cho and my Poddar. And we consider more general situation. So here actually I have to explain what are Lagrangians we consider in this context. And that is, this one is actually due to Chen and myself and Biden Wang. So today I just want to consider this. Okay. So I start from this, the maybe Gromov-Witten theory. So here I consider symplectic manifold such by X omega. This is a closed symplectic manifold. And then I pick J. It is almost complex structure compatible with omega, like a Keller form and complex structure, but without assuming integrability of complex structure. And then we can talk about holomorphic curves, like you have a Riemann surface here, and then consider some map you trace. So it is maybe called the Gromov-Witten map. If this one is differential is complex linear, so here maybe I denote small j, the complex structure on the domain, and then capital J complex on the target, and then the condition is just j du is equal to du with j, just the complex linearity. And so if we consider more general situation, like this sort of nodal curve, so at worst, so we just consider some even singular object, but at worst nodes or double point. And then we may also consider a bunch of mark points on it, like Z1, Z2, Zk. So these are the mark points. And mark points are distinct from nodal points. And also those points are mutually distinct. So we just write it like some sigma and then this G vector like this. And then consider mapping to U. We can also consider geochromatic map, namely for each component is such as this. And then at this node, actually the value coincide, namely first you have continuous map, and then for each component, irreducible component, you have this equation. And then you have this kind of mark point. So far mark point doesn't really make sense with this. But now we consider the automorphism of this guy. So automorphism in this case is the following. So I consider what is automorphism of this. So phi is actually biholomorphic automorphism on the domain, and mark points are also preserved. And also phi in commute with this. So I have a map U, and then I apply phi to back to itself, and then compose with U, and this is this. So this is a automorphism. So phi is automorphism. You have a automorphism of the domain with marked curve, and then the map is consistent with this phi. And we call it a stable map if this automorphism is finite. So in this case, actually, it does matter whether you have this mark point or not. But anyway, so this is it. Okay. And then next I consider so-called moduli space of stable maps. So let G be genus. And then K is just a number. And take A from the homology class of this manifold. And then we can talk about this M of G K A. So this is stable map. In this case, I only consider holomorphic ones, stable map. And also assume that this U star of the fundamental class sigma is equal to A. Then we have equivalence relation. Namely, if we have some mapping from sigma 1 z1 bar z1 vector to sigma 2 z2 vector, so that this u1 and u2 are related by that such a bihomologic map, then we just identify them. So we have this. And so this one carries so-called virtual fundamental class. And then we can define so-called Gromov-Witten invariant by the following way. So let alpha 1, alpha k from the homology class of this ambient manifold. And then you may consider alpha 1, alpha k of G, and K, and A by the following formula. So here is this M, G, A, A, and people may write buffer, and then this everyone star alpha 1 with every star alpha k. Maybe better to write it as a half product. So here we have evaluation map, right? So from here, actually, we have an evaluation map of J to X. So this guy is sent to U of the J. So J is from 1 to K. So I have a K marked points and then take values at this point. And then we have this map. So now you have cohomology class and then you put it back and then just do this integration. So ask is actually how to make sense of this. But today I don't want to say about this. And also if you want, you can also consider the certain forgetful map. I mean, just to remember the domain and then collapse all unstable components. Yeah, maybe. So if is it just a domain curve? So even the domain curve maybe have infinite many automorphisms, continuous automorphisms. Here actually, if this condition is required, then it is finite. So if you drop this condition, then there may be infinite many automorphisms. And then if you have such infinite many automorphism or continuous automorphism, we call it unstable component. And then here actually we just collapse unstable component. And then we get a moduli space of stable curves. And then, so maybe this maybe forget. Then certainly you can also take some cohomology class here, and then you can also consider the product with the pullback form and so on. Or maybe you can also use tautological classes and so on. But anyway, so today I just do this. And then the quantum cohomology is defined by the following rule. So this one is actually as a module. So this is just a cohomology. And then here we have a pairing, right? So you have two classes, alpha and beta, and then you can define the cup product and then take the relation with the fundamental class. So you have this. So now if you have this alpha 1, alpha 2 from this cohomology, and then we want to consider alpha 1, alpha 2, then I want to write it equal to the linear combination of element in these things, but it is enough to know the pairing with other elements, because this one is non-degenerate, so therefore it's enough to know this. And then this one is actually given by that one. So this is actually sum of alpha 1, alpha 2, and alpha 3. And in this case, actually, I have genus 0 and 3 map points and A. And then I put some decorations. And then E to the of, sorry, C1. C1 of X paired with A. Yes. So these two are actually indeterminate. I will tell you later. So then you just sum them up. So sum them up. So what is this? So these two are just some variables. So I introduce some ring, which is actually given by the following possibly formal infinity sum. And AI, today maybe I just consider AI maybe rational number or maybe real number or complex number, just something like this. And lambda I are just a non-negative real number. And di are just integers. So that lambda I, if there are infinite many lambda I require this actually diverge to infinity. If there is finite, only finite, then such condition is not necessary. But if there are infinite many of them, then I require this. So this one is I may just write in this way. There are no group here. So this is actually ordinary. This one, but tensors. This. So this is a finite dimension thing, and then take a tensor product of this to get it. So I have 3 elements from here, maybe times 1. And then I define the structure constant by this formula. So this right-hand side is actually living in this lambda zone. And if you want, if we can also take another element.
So you're saying that X is a manifold or orbifold?
Manifold.
Okay.
Manifold. I haven't really come to the orbifold case. And so I take another element. Maybe for easy case, maybe we take the positive part of this. If I take this positive part, that is if I take this positive, that is actually I only consider positive ones for simplicity. So for these things. And then we can also consider something like gamma here. And in that case, actually, this one is maybe replaced by this thing. So L many things, then 0, L plus 3, and A, and the same decorations. And here we have also sum over A and L, but then I have to model by L star. Then the same decoration. So this one is yes, maybe I have to write it in this. So alpha 1, maybe gamma, alpha 2, and alpha 3. So we have a family of product structure parameterized by the element from here. So this is so-called big quantum cohomology. So I just talk about this side, and secondly, come to this. So now I consider Lagrangian submanifold inside this. So this is a closed Lagrangian submanifold equipped with. So today I may just omit this relative, just a honest spin structure. More generally, we have a notion of relative spin structure, relative structure inside of this. But for simplicity, today I just consider spin structure. So L is this with spin structure, specific spin structure. You pick one thing. And then I start constructing so-called filtered infinity algebra over these things. This thing. So now this one, in this case, it is not just like a tensor product, because the differential for space for differential form is actually infinite dimensions. And so maybe better to say that this may be just written like a omega I and T of lambda I and E of di, and then lambda of I, and this one is lying with this. So instead of this scalar here, I now consider the differential form there. No, so therefore, I define this one by the correction of this. So this is the definition with this property. And then what we want to consider is the following. So here I take, yes, I take this cohomology class. And here I take relative cohomology. Maybe often we denote by beta. And then we consider the following things. So sigma d sigma is now, first I consider here just Riemann surface. So therefore here, first we consider just Riemann surface with boundary. And then consider map to XL. And then therefore, namely boundary is mapped to this L. And then we consider, yes, more general situation. So first case is just this Riemann surface with boundary. But today, or maybe for this purpose, we only consider genus zero case. So genus zero case. And so the first one is just a disk and the boundary of the disk. And then this is mapped to somewhere in the manifold X. But here we have a certain Lagrangian submanifold, and then the map is look like this. So the whole thing is mapped to X, but the boundary is mapped to L. So this is U. Right? And secondly, we may consider more general situation. So maybe I have disk, this kind of configuration of disks. If you take a dual graph of this, certainly you have this, right? So this component is here, and this component is this is this, and this is this. So we consider tree-like configuration of disks with the simple nodes, the boundary node. Okay. And it may have sphere component attached to this. It's okay to have this sort of things. So I have a disk and P1s. And then we have this sort of configurations. And then we also put some mark points. So now I consider Z0, Z1, but ZK on the boundary. So I have here maybe Z0, Z1 maybe here, Z2 here, Z3 here, and then ZK here, like this. So we have a order, cyclic order on this boundary. And so I just take Z0, Z1, Z2 in this cyclic order. And then possibly we may also have interior map points. So that may be here, or maybe on the sphere component, like this. So this sort of configurations. So I now consider sigma and boundary, and then I have this Z, and then this Z plus or something. Again, we can talk about automorphisms. So automorphism of this surface preserving this map point. And now I consider also U here. So sigma is mapped to X and boundary is mapped to L, and we assume this is J-holomorphic. And then these families of points may map to somewhere, but this. And we call such a thing bordered stable map if again this U, right? So U sigma D sigma D plus going to XL was stable map if this automorphism group of this guy is finite. We have only finite many examples. So this is the definite border stable map. And then we consider this M again. So now G is 0 for story. And so we have only map points. Today I only consider K plus 1 and L and beta. So you consider the space of border stable maps, modulo this equivalence relation, then we can consider certain kind of modular space. And here, I say this is K plus 1, because, yeah, at least as first part, actually, I only consider case that this is bigger than equal to 1. And in this case, actually, we can say that this is actually compact. And if it is actually 1, no, if there's this one is 0, no boundary mark points, then we need a big care about this compactness. But if we have one boundary mark point, and then, yeah, in this case, we have a compact modular space. Again, we have a bound map Fj to L and Fy plus to X. Okay. So now I want to define some sort of infinity operations grouped by this. So this one is omega star L tensor K going to omega star L. And if you want to make this operator degree 1, then I have to shift degree by 1 both sides. But maybe today I don't really pay so much attention to this point. So therefore, later I may just drop this shifting, degree shifting things. So this one I want to briefly mention. So if K beta, so exceptional case is the following cases like 0, 0, or maybe 1, 0. In this case, we just take MK, so M0, 0, say, is equal to 0. What is M0? So M0 beta is actually here, no nothing. So therefore, maybe we may consider it as a C or R to this omega star level. 0 power, like this. And so then we have 1, and then 1 is mapped to this M0 beta 1. So this 1 is, maybe later I also use this 1, but different letters. So this is actually for the unit in this ground ring. Okay, so this is 0, and M10 is equal to exterior derivative. So namely K equal to 1, and then I have just omega star L to omega star L, and the first one is actually D. And just Ruan differential. So I did some computation at that time, actually I asked D. And then I have another MK beta that I will define later. But for some purpose, it seems that maybe better to define to minus D, and then also multiply minus 1 to all the operations. But then actually I just use this convention. Okay. So now otherwise, so how we define it? Okay. So think it's not necessary anymore. So I just erase this part. Yes. No. This is definition. I just put it in this way. So these after I want to define this, and then these two things we just set. Yes. Okay. For other ones, we use this modular space. In particular, we use this M K plus 1 of beta. So it has a lot of evaluation marks, right? Maybe I wrote it F equal to F1 rather than Fk. So this one is going to L times F. And then I have another one that is F0 going to this. So now I consider differential form on this. So now I consider, say, differential form on this and differential form on this. And then somehow also want to consider differential form on this. We have to make sense of this, but today I don't want to pay so much attention to this. I don't really spend time on this. So what we want to do is somehow you have a differential form here, like psi 1 cross product with this psi k, right? And then put it back to this space, and then push out to this. So what we want to do is somehow F0 sweep, and then this F star of psi 1 psi k. So this is the definition of this mk beta of psi 1 psi k. Okay. This is just sorry. I need to put some sign here. So here is some sign convention. So maybe if somebody is interested in this, maybe I can also tell you later, but there is some signs. And one more thing is that, okay, so I assume that this is actually equipped with spin structures. So not just a spin manifold, but spin structure. This spin structure somehow gives us orientation of this space. And L is oriented. So pullback is okay, but when you push out, no, that's another thing. So if you, even though it is submersion, you need a orientation along fibers. So, but now we have these kind of two things oriented. So we fix some convention to orient the fibers. So maybe this part is a little bit difficult, so I don't really say, I take some time, so therefore I don't say this. And another thing is that, so if you have a map, like even the manifold case, you have a manifold M to N, and you have some smooth map like this, then here in general, you can really define this. So this is okay for submersive case, because it integration along fibers. But otherwise, it is not. So what we do is actually we use so-called continuous family of perturbation technique. In other words, no, I will tell you later. So today I don't, at this moment, I don't want to spend time on this. So our technology somehow, yes, this Gromov structure technology says that from this one to this one, so we have a Gromov neighborhood of this guy, and then over this Gromov neighborhood, this one becomes submersive. We can have such a thickening. And then we take a family of perturbation. So then we take this sort of things, and then using this somehow we can actually make sense of this integration of fibers. So this one depends many choices. Actually, this one depends on the choice of the CF perturbation and so on. So, but anyway, so this is one point, certainly, but I wanted this. And then this one satisfies the infinity, so-called infinity relations, because the following. So the infinity relation actually follows from the following, sorry, this way. Following reason. Sorry. It's very hard for me to use this. So maybe stop it. So we have the following type of operations. So like, okay, so maybe before this, I may define this. This one is equal to the sum of mk beta to t beta omega and e to the mu of beta. So mu is actually mass of index. So sorry, I have to say this. So I define this way. So it's a kind of formal things, but degree of P is equal to 0, and degree of E is equal to 2. So it's a graded ring. And so this part actually takes care of mass of index. And this is the energy or area of the Gromov curve. And then I just take this thing. So then this one may be infinite sum, but it converges in t-adic sense because of Gromov compact. And so this one satisfies so-called filtered infinity relations. So this one, maybe I just write it in the terminology. Then I consider this mk prime beta prime, maybe psi 1 that something, and then mk double prime beta double prime, and psi j psi j plus k double prime minus 1, psi k is equal to k prime plus k double prime minus 1. Okay. And then you take, so this one is just a cosine sign. So C1 to psi these things, but we have to put degree after shifting. So therefore, we just use some shifted degree and cosine, but the shifted degree. And then the sum of this is equal to 0. For k prime k double prime is equal to k plus 1, and beta prime plus beta double prime is equal to beta. So k and beta fixed, any k beta, and then I consider all possible such decompositions, and then consider this is equal to 0. So this is filtered infinity relations. And the reason why we have this is the following. It actually follows from basically following two facts. So one is the boundary of the moduli space of this holomorphic disks or border stable maps. Okay, so first one is this. So I consider this m, k plus 1, and beta. And then look at the boundary of this. And this boundary somehow written as here actually we need to sign. Today I don't want to say this so much. Okay, prime plus 1 and beta prime. And here we have j, we have 0, and m k double prime plus 1, and beta double prime. So namely, so here you may have just a holomorphic disk like this. And then if some sequence of such holomorphic disks converge to the boundary point, so namely this one may be getting like this, and finally it may split into two parts. So if you do some computation, just the formal dimensional computations, except dimensions, actually this happens in codimension 1. If in the Gromov-Witten theory, such degeneration happens in complex codimension 1, that is real codimension 2. But in this case, actually, real case, actually, it happens in real codimension 1 for these things. So this one is maybe in element in this, maybe mk plus 1 beta, right? And I have a bunch of map points like this. I have a bunch like this. Here I also have bunch of map like this. And this one is actually class beta, and this one is class beta, but here actually it may split into two things, beta, beta double prime, and here maybe Z0 here. And then I have k prime many mark points, k plus 1 many mark points, and here I have a k double prime plus 1 mark points. Yes? That is codimension 2. That is, no, that is codimension 2. So this one also included, but somehow this one is codimension 2. So we can also include it. But yeah, actually this one still we may consider it in this part. Yes. So therefore, this one may split into two things, and this thing is an element in here, and this thing is element here. And here the this mass point, value at this mass point coincides with the zeroth mass, the value of zero mass point as the first one, second one. So therefore, it's a fiber product of these two things. So this is the first thing. So this actually, if you consider this kind of operations, then this one taking care of this mk double prime beta double prime, and this one taking care of this mk prime beta prime. So somehow this sort of thing can be represented by this. But another one is the following. So now I consider this M is a manifold, but manifold with boundary set. This is, we have to really work with this, but I have to a little bit more easier situation. So I have some submersion. So here actually proper submersion here. And then let's suppose that on the boundary, if you discrete this boundary, this is also proper submersion. So let's consider such situation. And then start from this omega star of n, maybe some difference from xi. And then I just first use this pi to push this xi to downstairs. And then maybe I take extra derivative here. So then I need to take signs, but this one is equal to pi 3 of dxi. And then we have finally maybe this sum is equal to 0. So if B is a point, this is just Euler-Stokes formula. If B is a point, then we don't have this term. So first you take this D and then integrate. That is same as integrating on the bound. But now we have this vibration situation, then we have this. And in our case, M10 is D. So therefore, this one, play the role of M10 here and here. And then these things, now we use these things. So if you just combine these two things, then in fact you may end up this formula. The sign checking signs a little bit involved, but somehow it works. And so first we have this, and today I just stop here because I want to go to this part. No. The next time maybe I may come to this again and say a bit more about Malloy-Cartan element, or maybe with Malloy-Cartan element, potential functions, and so on. And also, here I say that this is mk plus 1L. So far, I didn't really use any component with non-zero L. But we can also have the following things. Maybe I just mentioned this. But in fact, we have this Q, K comma L, beta. So L comma K beta. I don't know which one is better, but okay. So this one is somehow like this. Maybe in this case, shift by degree by 2, and L, and then omega shift by 1, tensor K, going to this omega star L to 1. So in this case, so now we consider L is no negative case. L equal to 0 case, it is our this M, right? So Q K0 beta is nothing but this M K beta. And then I consider this. And this one is also defined the same way. So F0 streak. And then first I have F plus star of say eta 1 eta L. And then wedge with F star of psi 1 psi K or something like this. And then I need to put some certain sign here. So this is the definition. So this one here I have eta 1 tensor eta L, and here psi 1 tensor psi L, psi K, and then we want to get something output here. The output is actually given by this formula. So not only print back differential form from L, but also we pull back differential form from the interior of this. And so one thing I have to say is so-called bulk deformations. So that's why I mentioned a little bit about this big quantum cohomology. Yes, still manifold, still manifold. I never say anything about it. So let's take B. Maybe it's a cycle in this X with maybe lambda plus coefficient. So I take this. And then we want to consider this M, B, K, say beta. No, this is no good. This is maybe better to write it in just this way. So if I have one to xi 1, xi K, so we define it by this Q. So maybe I need to have a inverse L factorial times Q KL, and here I plug in B L times, and then xi 1 as a xi K. So I explained that not really completely, but somehow if I define MK beta in this formula, and then look at the boundary of this modular space, which is written as a union of fiber as a fiber product, and also we have a kind of Stokes type formula from these after we have infinity relations. And so here actually we have some additional things here, and you can do the similar things. And so we can define some property for this QKL. Now we plug in B as many times as you want, and then sum them up. And this one also gives you filtered infinity structures. So this is what we call bulk deformations. Oh, no, this is done by this. Take it at intersects. So this one is useful for some application and also theoretically. And this is how to say. Yes, today I may stop here, but maybe if you remember how the quantum cohomology is defined and how big quantum cohomology is defined. At that time, structure constant, I consider alpha 1 star alpha 2 with alpha 3. Then I have a 3-point functions. But we want to consider alpha 1 star over gamma, star gamma, and alpha 2 and alpha 3. And then we have sum of L plus 3 point functions over L factorials divided by L factorials. And then some this gamma appears L times, so arbitrary number of insertions there. So this is very similar things. In a sense, same type of argument. So there actually associativity of this quantum cup product is shown for any gamma, and here this one is a filter infinity structure for any B, if B is a cycle. Okay, so I just stop this manifold story and then come to the orbifold story. What? I come to the orbifold case. Because this is, no, I don't know. I'm not good at this, so. I don't want to say so much about orbifold, but somehow, because orbifold is already somehow well studied in many places, so may not be so necessary, but maybe I just want to come to this. And so this notion was certainly first introduced by Professor Satake under the name V manifold. And this is V stands for bifurcation in German. So Verzweigung, bifurcation in German. So that is the reason why Satake called it V manifold. And so this is kind of space locally modeled on this kind of stuff. Well, gamma is finite. Maybe you can consider the finite linear. And so for the manifold, you have a manifold. You can cover it by chart. Right? So you can just have a chart. I don't know, maybe you have a chart. So here is a coordinate system for these kind of Euclidean spaces, and then this one up to this, and this one up to this, and then the overlap you have a coordinate change that may be phi beta alpha or something, and then this is maybe psi beta and psi alpha or something. And then if it satisfies the co-cycle condition, you have a manifold, right? Just this. And for orbifold, so you have any point. So you have so-called uniform wisdom cover. So this is actually uniform cover. So now it is not really kind of homomorphism, but it kind of quotient by some gamma. So gamma I or something, right? So maybe this is UI tilde, and this is UI. And so this one is contained in certain Rn, and then gamma I up here, and a group, and then this kind of stuff. So if you have another one here overlapping here, then you have another things, maybe gamma J here, and so on. And then what is the compatibility? Was this kind of, here actually you have a coordinate change. But here maybe gamma I, gamma J are completely different group and so on. But then I take any point. Then I take some small neighborhood of this. And this one may also have another one like this. Maybe also gamma gamma k or something. And then, so you have this yellow one contained in this side and contained that side. And then it can be lifted to this side, right? This one. So this one maybe also like this, is this. And then I don't know how to write it. Maybe this one will map to this, or maybe this one map to this. So inverse image of this guy may consist of several copies of this, like this, right? But just take this one, map to one of them. So like this. So this part is actually just a diffeomorphism. And here we have a gamma k, and then gamma k. And here actually the group is gamma j. So therefore we need a homomorphism, maybe even injective homomorphism from here to here, and also injective homomorphism to gamma. And then we have, say, inclusion here and here. And then this one is actually equivalent under this homomorphism, and this one is equivalent under this homomorphism. So that kind of thing is a orbifold. And then if we want to define some notion like a differential form, a vector field, or almost complex structure, and so on, then you just define it as a such gadget which is invariant under gamma. So here you have a differential form which is invariant gamma I, and here you consider different form invariant gamma j, so that they actually matches in this intersection. So on. Then you have such a notion. Almost complex structure, you can also do this. And you can also define tangent boundary and so on. But in fact, this notion is okay. This notion is okay. And it depends on your purpose, whether you want to find something different from this. So as I said, we can define the notion of vector bundles, or maybe tangent bundle, cotangent bundle, so on. But here actually I consider the holomorphic maps from this Riemann surface to the symplectic manifold, which is J-holomorphic and so on. So now we also want to consider such a kind of stuff. Domain is actually orbifold Riemann surface. Target is a symplectic orbifold. And then take almost complex there. We want to consider this holomorphic maps. And then when we usually study the modular space of holomorphic maps, certainly first we consider certain Fredholm setup. Like locally, you just pull back the vector bundle, tangent bundle to the domain, and then consider a section of the domain with WKP sections of the domain of that thing. And then this actually gives you a chart in the mapping space. So somehow we need to consider such a pullback of vector bundles. And then in order to pull back vector bundles, somehow the notion of morphism between orbifold should be considered in an appropriate way. So for that purpose, actually we may use the presentation by proprietary group. So Chen and Ruan didn't really write in that way. So they still work on this kind of things. And then domain and target. And then they gave a very complex kind of introduce a notion of good map. Yes, but good map, the notion of good map, they introduced for that purpose. But now I present it in a different way. So in fact, this is a fact that orbifolds are somehow presented by so-called proprietary groupoid. So what is groupoid? Certainly, as you know, groupoid is a category so that all morphisms are invertible. And here actually we consider the space of object and space of morphisms, both of them supposed to be manifold. So I consider X. So now I have X0 and X1. So they are manifolds. This is a space of object, and this is a space of morphisms. And then we have a bunch of smooth maps. So they are smooth maps. So I assume that they are manifolds. They are actually manifolds. They are smooth maps. So first, we have this space of morphisms. So therefore, you have two maps. So some target is this. Sorry. So morphism from one object to another object. So therefore, this you have source map and target map, and we assume these are smooth maps. And also, we require that in the case of just a D group void, and then we may assume that they are submergents. Maybe you may assume one of them is submergent, and then later you may see, because of this I, another one is submergent. But anyway, so this. And once you have this, then I take a fiber product. So I have x1, and then consider the map to x0 by target map. And then this is another one to the source map. And because one of them is enough, but both of them are submergent, so therefore the fiber product is a manifold. So this is a manifold. And then we may ask, this composition of morphism is also smooth map. And then, so U is a unit. So x0 to x1, it's a unit. So this is a smooth map. And then we also have an inverse. So this unit. So this is actually a composition. Then certainly I have to assume that we have to require associativity. Certainly, otherwise it isn't. So this is a legal void. And proper means that proper means that x1 going to s3 going to x0. X0 is actually proper. So just like this. And eta means that this S and T, or maybe one of them, is actually local diffeomorphism in this case. So this is one. So here, if you have this kind of system of such a uniformization covers, then you take a union of these the uniformization covers. That is space. That is a space of object. And then you may have group action here, or you may have this kind of injection here. That gives us morphisms. So therefore, you have this. And in fact, any proprietary legal void, so this proprietary legal void is locally the following form. So here is a finite group gamma, and then here you may have some U, maybe some open set, maybe just a manifold, or maybe domain in RM, and then this kind of actions, and so that we have this groupoid, so-called action groupoid or translation groupoid. So what is this? So this consists of two things. So one is this 0. It's just a space of object that is U. And then I have a gamma U of 1. This is actually gamma times U. So this is a space of object, and this is a space of morphism. And so what is the structure maps? So maybe I don't need to say so much about this. So here you have element is actually given from here. So therefore you have gamma and x. And then the first map is just going to x, and second map is gamma x. And multiplication is also something similar. Gamma x and gamma prime x prime. It is defined when gamma is equal to gamma prime x prime, and then this one is equal to gamma prime of x prime, right? So otherwise we don't define it. And the unit is actually just x go to identity and x, and the inverse, maybe inverse of gamma x is equal to gamma inverse and gamma x. So you have x, and then you have gamma x, then you have some arrow here, and then we want to have inverse arrow, so therefore from gamma x and gamma inverse. So okay, so this is the local presentation of this groupoid, proprietary groupoid. Ah, already? Okay, then I cannot say anything, but then maybe I can continue next time, yes. No, maybe 5 minutes, maybe. Okay. So somehow we want to consider these symplectic structures. So symplectic structure is actually a pair of. So okay, symplectic structure or maybe any. Okay. Maybe I just want to say this. So if we want to consider certain geometric object, on this thing, and then how we can understand it. So this one is, in a sense, this geometric object on x0 with x1. Like, so differential form is very okay. So, but maybe I consider some vector bundles. Okay, so vector bundles, like vector bundle, maybe this, I want to have vector bundle over this. And then this one is somehow I consider this x0. Then over here, I consider e0. It's actually vector bundle. And then I consider this x1 going to x0, e0, going to e0. Maybe I denote pi. Maybe this is pi, and this is source. So this is the action of x1 over e0, and with multiplications ts s pi e0. Then we have two maps. So one is just taking first one and then this one, and then first I have this multiplication stuff, and then I have this, and so therefore this one going to E0 by this action, maybe I identify phi. Another one is somehow we consider this one is x1 cross E0 and phi and S and T. And then here I use this phi. So therefore, this one is now coming to x1 ds of E0. And then again, phi, you have this, and then you assume this quantity, like a product structure on this groupoid and action compatible. So this is the vector bundles. So now if maybe I have 5 minutes, you said, so do I have 5 minutes? Yeah. So then I take the definition of morphisms. Okay. So here I have one that's a proper any groupoid, and Y is another groupoid. And if there is a functor, so in our case, after we consider the maps between objects, the maps between morphism are both smooth, but anyway, we have this. And then certainly we can make sense of this. So you have this. Sorry. Oh, sorry. Maybe better to write it. If I have this vector bundle, and then you can prove back by this. So this is actually not so difficult to see. But when you consider mappings between manifolds, you have a given chart, and then this open coordinate chart may not be mapped to one coordinate chart. So therefore, you have to take a refinement of this. So in general, we have to take a refinement. So you maybe certain refinement. Maybe next time, maybe I may start from here. And then the general definition. So X to Y. So this morphism is in fact defined by this. This is the refinement. And this is actually straight things. Sorry, Y. So this Y is in this sense. And this Y is refinement. And for instance, if you pull back the vector bundles, you can pull back this. And if it is refinement, actually, if you have vector bundle over here, somehow you can use this information to get the vector bundle over here. Like this equivalence of equivalent categories, and so therefore you have something, and you can also get something there. So somehow in this case, actually, you can pull back vector bundles. So I haven't said anything about this part, but anyway, so in order to say a little bit about this, I need this notion. So therefore, maybe next time I may start from here. Okay.
Thank you very much. Question, Roman?
Yes. 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 In fact, yeah, at that time, certainly this one already introduced, maybe in late 50s or something, or maybe 60s. And certain story maybe 70s, late 70s or 80s or something. But nobody in the audience knew this. Even though there was a Japanese. Some Japanese one was actually in the audience, but he didn't know it's V manifold. So therefore, maybe he agreed to name it as object. But yes, so V manifold. So as I said, somehow people may be curious what V stands for. So this is V is after Hertz-Weigen.
The only one question about the defining filter infinity structure
Yes.
through the push arm and pull by.
Yes.
There are some that is a kind of completely new construction when you open with the Lagrangian integration theory or that's a
No, no, no.
how you can do this. There is some kind of motivation similar construction.
No. This, I think this is just a correspondence.
Correspondence.
So correspondence is kind of old ideas.
Yes, that must correspondence for every old stuff. But every time it doesn't have correspondence, then it will define the infinity structure.
No. So somehow, in fact, this algebraic structure appears because of the underlying structure of the domains. So you consider this disk with quantum map points. So you consider such a modular space. And then consider how it decomposes, how it degenerates, and so on. And then that one is actually, in a sense, essentially so-called associated. I mean, this. Yes. So therefore, in this story, actually, the structure comes from, in a sense, structure of the domain curves. And so this is actually okay. That's similar to this quantum product and so on. That also comes from this. And pullback is certainly, in a sense, okay. Although I didn't say anything about this modular space. What kind of structure do we have? But if we have some sort of chart, and then you may expect that there is no some differential form and so on. But the problem is somehow how you push out. And maybe I can tell you later. So locally, yes.